The grand shrine of Ise in Honshu, Japan was likely first constructed about 2400 years ago. It is home to Amaterasu, the sun goddess. The shrine is at the heart of Japanese culture. That was until recently. Amaterasu is now also a rare and extremely high energy particle which fell to Earth on May 27th, 2021. The discovery of Amaterasu is utterly mystifying for particle physicists and astronomers because they cannot yet tell where it originated except that it may have come from an empty part of the universe. It is most likely extragalactic in its origin, meaning outside of our home galaxy, the Milky Way. There are those who think that Amaterasu has the potential to fundamentally alter physics. To understand the particle, Mayank Chhaya Reports spoke to Professor John Mathews of the University of Utah and a co-author of a paper just published in the journal Science about the particle, Professor John Mathews. Welcome to Mayank Chhaya Reports, Professor Mathews. It's a great pleasure to have you on.
It's a pleasure to be here. Thanks for the invitation.
You posed a profoundly scientific question, which said, "What the heck is going on?" When you when you found out about Amaterasu, the rare and extremely high energy particle that fell to Earth. So, what the heck is going on?
That's the question. That really is the question. So, what we're talking about here is an extremely energetic particle. So it has about as much energy as a fast pitch baseball, or if you held a lead brick, not a ceramic brick, but a lead brick up at your waist, and then dropped it down on your toe, let's say. You'd feel that, and that's a huge amount of energy being deposited there. So it's a huge energy. It's in a tiny particle. It's in a proton, probably. So at that energy, particles should not be able to travel far. When I say not far, I mean like 50 or 100 megaparsecs, which seems huge.
Yeah, it is.
But it's only the size of the local supercluster of galaxies. So optical telescopes would say, "Oh, that's close by. That's our neighborhood."
Right.
So if it was further away than that, then it has high probability that it would have collided with the microwave background, which is the photons left over from the Big Bang. They're like 3-degree Kelvin photons. They're everywhere. So in colliding with the microwave background, it would have produced a muon, and that energy had to come from somewhere, and that energy comes from the kinetic energy of the proton. And so the what would happen is the proton would come and collide with the microwave background and lose its energy, and so you wouldn't still have this much energy. So it should come from someplace close. We look at where this particle, the Amaterasu particle, or the oh my God particle, where did they come from? And you look back, there's nothing there. It's a mystery. This new particle comes from, in fact, the local void just next to our galaxy. So what the heck is going on? So there's nothing there. Should have come from someplace close. What are your choices? Not a lot of good choices. Maybe it's more charged than you thought. Maybe it's not a proton. I would say probably it was, but let's say for the sake of argument, it was an iron nucleus or something. Then it could have been bent a lot more than we thought and come from someplace else. If the magnetic fields inside or outside the galaxy are a lot stronger than we think, that's a possible choice. maybe there's some way to defeat these collisions with the microwave background. Some people have proposed that if you go up to really high energies, like 10 to the 21 or 10 to the 22 electron volts, then maybe you can get around those collisions. Uh, could be that there's some massive particle out there that we don't know what it is, and it's decaying to these particles.
I see. Was it fair to say that at this stage you suspect that it is extragalactic in terms of its origin?
Oh, yeah, I'm pretty sure it's extragalactic. There's nothing in this galaxy that looks like it's that big and that violent that can uh, make such a particle.
Which would mean that it would have traveled billions of light years, right?
Well, means it would have traveled a long way.
Yeah,
uh,
no,
I, I can't really say how far, but uh, I certainly think it's from outside this galaxy.
okay. The reason I'm asking is for it to travel so much and still retain the kind of energy that you're talking about. That's extraordinary, right?
Yeah, I mean, to accelerate a particle to this kind of an energy, you need a huge violent object with really high magnetic and electric fields, high electric fields to accelerate it, high magnetic fields, and a large area to constrain it while it's being accelerated, and then it has to somehow get out and find its way to us.
Do you think the Milky Way is capable of creating a particle like that? Is there anything in the Milky Way that can create something like this?
I think the Milky Way is really only capable to generate particles up to maybe 10 to the 17 or 10 to the 18 electron volts. So it's well shy of this energy.
I see. I see. In the interest of clarity, this was a sort of a shower of Amaterasu, right? It's not. I mean, it's not a single particle.
Well, it's a single particle until it reaches the Earth's atmosphere.
Oh, I
So,
see.
so what happens is a cosmic ray comes to the Earth, and high up in the atmosphere, it collides with the nucleus of an oxygen or a nitrogen, something high up in the atmosphere. And then that splatters that nucleus. You get a bunch of secondary particles. And those secondary particles travel a short distance, and then they do the same thing. They collide with another nucleus of something high in the atmosphere. And so what you end up with is what's called an extensive air shower. So you end up with billions of secondary particles. And so at telescope array, what we have is two types of detectors. One is some telescopes, there's 60 telescopes actually, that sit and look out more or less towards the horizon in all directions. And what they're looking for is that shower of secondary particles. They excite the gas of the atmosphere, and that gas, when it de-excites, it emits fluorescence light, which is mostly in the ultraviolet. So the telescopes look for these ultraviolet light tracks coming down through the atmosphere, and you can look at how the shower develops, look at the longitudinal development of the shower.
I see.
And the other thing we do is we sprinkle the floor of the desert with scintillator detectors. So those are plastic detectors that emit light when charged particles pass through them. And they're about the size of a ping pong table.
I see.
And we put hundreds of them out in the desert. The original array was 500, and we're in the process of putting another 500 out there.
I see.
And so they're spaced about every 3/4 of a mile, 1.2 kilometers. And When the shower comes down, it's got a huge pancake footprint, and those detectors measure the density of charged particles at their location. And a typical shower might hit several of these detectors. This shower was so energetic and so many particles and spread out so far that it hit 23 detectors. So it's covering a huge area.
Right. Right.
And when that pancake comes down, there you can imagine there's a detector here, here, here. And so the angle that it comes down at, you can use the timing that it hits each detector to point it back to where did that thing come from.
Right.
And you measure the amount of light each detector sees, and then you can look at the footprint and what that looks like and figure out what's the energy of the primary particle.
You mentioned that it's scattered into billions of secondary particles. Now,
Uh,
how do you work back from that to a single particle? It's fascinating for me. How did you do that?
so you have simulations that are based on accelerator experiments. And so you can use what's called a Monte Carlo. It's called Monte Carlo because basically you're gambling, right? You calculate the odds that anything's going to happen in a shower, and so you start by simulating one particle and it collides, makes a bunch, then travels. So you're simulating the whole shower. How does that develop? And then you can scale that with energy. And the problem is, I mean, this is actually quite a good technique, but it does have its limitations and problems. And part of that is due to the fact that the accelerator experiments really only go up to about 10 to the 12, 10 to the 13 electron volts, because that's the limit of man's technology.
Right.
So even you go to the Large Hadron Collider, you're only at about 10 to the 13 electron volts. So now you need to extrapolate that out to 10 to the 20th electron volts, or in this case, 2.4 times that amount. So the distribution of particles and the uh, sort of reconstructing the energy, it sort of scales, but uh, there are some problems. And in fact, in you know 20 years ago, these reared a nasty side effect. So the previous experiment, like 2 generations ago of experiment, was the fly's eye, which saw the oh my god particle. The previous generation of experiment to this, here in Utah, we were running the high resolution fly's eye, which was just telescopes. And telescopes do have the advantage that they're just measuring that light, which is very proportional to the energy of that's being dumped into the sky, which is a big advantage. And simultaneous with the high resolution fly's eye, there were Japanese collaboration called Agasa, and they
Mhm.
were just using the scintillator detectors. And what we found out in the late 90s, early 2000s was our Japanese competitors at that time were seeing that there was no cutoff due to the microwave background. They were seeing lots of high energy particles. And the high resolution fly's eye, we said, no, 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 no. There's a cutoff here. Look, look. So in the late 90s, early 2000s, when we were sitting back arguing with each other, we also got together and said, let's build a bigger, better experiment, and we'll call it telescope array. And we'll put scintillators with fluorescence telescopes. And the advantage of that is that then you can use the direct measurement of the energy deposit. from the telescopes and compare it to what the scintillators are actually seeing.
I see. I'm curious, this is perhaps an ignorant question, but I'm going to ask it anyway. Couldn't this particle have been uh, detected by a space telescope as a single
Uh,
particle?
yes and no.
I see. Something like
So,
JWST, for instance,
like what?
the James Webb Space
Oh,
Telescope.
not the James Webb Telescope, but have you heard of the AMS?
Yeah,
So something closer to the AMS. The problem with James Webb is it's just looking at uh, optical and infrared
I see.
signals.
Okay. Yeah.
So
Yeah. Right.
it can't measure uh, charged particles. But AMS, it has the advantage that it's very much like an accelerator based particle physics detector. It has particle identification and it has magnetic fields so you can measure the charge, and it has a calorimeter. It's a really nice experiment, but the problem comes in that these really high energy particles, well, they're much higher than AMS is ready to deal with. And
Okay.
because of its limited size, it can only measure significantly lower energies, like I think 10 to the 14, maybe electron volts. And also at that energy, if you look at the cosmic ray spectrum, it falls very steeply. So at 10 to the 14, you can, the flux is a few particles per square meter per hour or something.
I see.
And
Okay.
at these really high energies, it's one per square kilometer per century. So you're never going to hit it, and it's going to pass right through without
Okay. That's
making a complete measurement.
right. This was discovered on May 27th, 2021.
Yes.
Where were you then?
Probably at work here.
Okay. And this is not something that uh, sets off some alarm or anything. It's a
Now,
process that you have to analyze over a period of a long time, right?
so typically we're taking data all the time, especially the scintillator array is taking data 24/7. The telescopes are only, because they're so sensitive, you're looking for 100-watt ultraviolet light bulb moving at the speed of light.
I see.
So they only operate on clear moonless nights. This happened in the daytime, so we only have the scintillator signal. But that said, the data is so sparse that what we do is we tend to collect several months at a time and really only analyze it in detail on a 1 year basis,
I see.
because the atmosphere is doing things and we want to make a spectrum and check that the data all looks reasonable and it's behaving and we didn't make any mistakes. So it would have been almost 1 year later when we would have looked at the data.
I see.
And then on top of that, then it took a long time to get the publication through science
Right. Right.
because they're very picky and careful
I'm sure.
journal.
Yeah. You've said, and I'm quoting you, you trace its trajectory to its source, and there is nothing high energy enough to have produced it.
That's correct.
Explain that.
Um, so you need to, you can trace it back by using this technique of timing. Each detector has its own GPS,
I see.
so you can point it back to where did it come from. But you would expect there to be like an object that might have enough energy and it might have enough high enough electric and magnetic fields, would be like an active galactic nuclei or something, where you have a black hole, but it's also eating something, maybe another black hole, maybe a bunch of dust from other stars or whatever. And you've seen these pretty pictures of stuff swirling in, and it's really violent. It's ripping things apart, and then there's big jets shooting out. You'd expect to find something like that there.
I see.
And yet instead of that, what we're finding is you're looking into a void where there's nothing.
But evidently there is something, otherwise this particle
Evidently,
would, yeah.
exactly. And what is that?
I see. That's quite absolutely discommoding. I mean, I'm troubled by what you're saying that it's a void and yet it produced energy of this level.
Like I said, maybe another choice is maybe we don't. There's maybe it's dark matter, and something is decaying. I'm not inclined to believe that, but you gotta believe something,
Yeah.
right?
What's your gut feeling as a scientist?
my my gut hope,
Okay.
more than a feeling, is maybe it was even more energetic and bypassed the microwave background and then snuck into us.
I mean,
That
just
was,
to,
so if you can start looking further and further back, maybe there's something back there.
to think that a single particle travels this distance, and I'm sure there's some dissipation of energy over a period of time, and there isn't.
There shouldn't be, except like interactions with the microwave background or other dust.
Okay.
And like if you let's imagine it started as a iron nucleus or a nitrogen nucleus, then along the way, in short order, it should have spalated or peeled off those other protons and neutrons and stripped down to a proton. So, you know, could have steered around, started as something, but it would have had to have been much higher energy to still be what's probably a proton when it
I
came
see.
to us, right? Because if that one proton has 2 times 10 to the 20 electron volts, when it was iron or whatever it was, would have had to be 56 times that.
Right. At a philosophical level, do you wonder why a single particle ended up here on Earth, of all places?
Oh, sort of like aliens. I feel like there's so many things out there, so many galaxies, so many planets. You know, there has, in my feeling, there probably has to be aliens out there somewhere.
I
But
see.
and in the same vein, not necessarily that they've been here, probably not, but probably out there there's other life. In the same way, some of those particles have to find their way to us.
Right, right. But this couldn't have been any sort of signal, right?
You mean from other life or
Yeah,
from
I mean
what?
it's something which is of artificial origin, but that's not possible of this energy.
I'm not thinking so. I tend
Okay.
to be my feeling is I tend to be the physicist and say
I
it's
no,
got.
I understand. I absolutely I'm with you on that, but I'm sure there are people who wonder that.
Oh, I'm sure there are, but I'm disinclined to believe that.
Okay. This had an energy of 224 electron volts
Mhm.
compared to the 320 that oh my God particle had.
Right.
I'll come to the question of nomenclature because I find sometimes ridiculous that these nomenclature exist like God particle and oh my God particle, but that's beside the point. The difference between 224 and 320, it's a huge one.
It's significant, but not huge. So the uh, and and one of my arguments along that vein is that I feel like they're in the same ballpark, and the fact that we saw the oh my god particle with the fluorescence technique, and now we've seen the Amaterasu particle with scintillators, and scintillators that have been calibrated by a fluorescence detector. I feel like I feel very comforted by this because I'm I'm thinking these are in the same ballpark. you've done this two very different ways. So this is really strong proof that these particles do exist and are coming probably from some place close by.
I see.
On the other hand, we have at telescope array something like 30 or 31 particles above 10 to the 20th electron volts. And because of how steeply falling the spectrum is, I'd say the ones that are down around 10 to the 20th, they're similar, but they're not really in the same ballpark.
I see. Do you
They
think
all
this is
tend
a
to be at the low energy end of that.
okay? Do you think it's a one-off event, or we could see more of it?
Oh, I'm pretty sure we're going to see more. And earlier I was saying the telescope array is putting more detectors out. We're presently trying to expand by a factor of 4. So I'm pretty sure we're going to see more of these.
I see. These days everything seems to have the potential to upend physics as we know it. It's been said about even this particle that it could fundamentally alter physics. It's been said about the data that the James Webb Space Telescope is producing in terms
Yeah.
of the age of the universe, saying that maybe our physics is wrong. What's your sense about this particular particle's potential to at least very significantly challenge physics as we know it?
Well, we have 30 of these particles above 10 to the 20th. If we expand by a factor of 4 and we collect, 4 or 5 times as much data, either we're going to find sources, in which case we can study those sources and that'll be interesting. Or if we don't find sources and they're still coming from random places in the sky, then now you've got a big mystery. You've got to solve that mystery. Is it decay of dark matter or other remnants out there that we don't understand what they are? Or are we somehow sneaking around the microwave background or what? So I think there's high potential here for something new and exciting to come out once we get a little more data.
Cosmic rays shower on Earth almost constantly, in a sense. What are,
Absolutely.
what are the challenges of sifting through them, and how do you think AI can help you in sifting through this massive data?
Well, two different questions, but very interesting ones.
Okay.
So at low energies, they can be coming from stars, the sun, wherever, 2 per second through your head. So the telescope array really only, because of how sparsely spread around the desert they are, we only start to see things starting around 10 to the 16 electron volts. And we're really focused at higher energies. How can AI help? That's really a good question, because up until not that long ago, mostly we used the events that we either saw using multiple telescopes at different locations, or what we call hybrid events, where the telescope sees it, but also the scintillator array sees it. And you can use that to constrain the geometry and then get a good measurement of the chemical composition of the cosmic ray. What we're doing more recently is actually using AI and machine learning techniques to try to just look at the scintillator detectors and try to figure out what the composition is from that. And there's 2 layers of scintillator in each of our scintillator detectors, and they have really fine timing resolution. They're taking like little movies of the event as they come in. And so what you can do is look at that pulse shape and what are the little peaks and wiggles in there, and compare the top layer to the bottom layer, and try to figure out which ones are muons and which ones are electrons. And that gives you some information about what the composition is. And now what we need to do is refine that technique and then calibrate it against the fluorescence telescopes. So
Just yeah,
that's
just
going
last
to
just last couple of things. One is I find the nomenclature practice in physics and elsewhere in science sometimes, uh, sorry, but ludicrous. Why would physicists feel compelled to use words like God particle or oh my God? I know it's
uh,
funny, but what's the point of calling them that?
well, the oh my God particle, somebody was looking through the data and looking at event displays, one event after the next, and they all look okay. There's a track, there's a track, there's a track. Not very exciting. And then all of a sudden they saw something that was huge, and he said, "Oh my God, what is
Fair
that?"
enough. Fair enough. Yeah.
The Amaterasu particle, it's more our Japanese colleagues who were looking at the data said this is a big particle, a high energy particle. It's shining light on some mystery. And so let's name it after the Japanese sun god, and
Yeah.
she shines light on things.
Right. In fact, that shrine is about 2,400 years old. The shrine where this goddess is supposed to residing. It was
Oh, I did not
constructed
know that.
2,400 years ago. This is in Honshu area of Japan,
Yeah,
and the royal family of Japan claims to have been sort of descended from there.
exactly. And they have like a sword, a mirror, and
Yeah, there are mirrors, 3 mirrors. You're right. Uh, uh, to conclude, this is again a broader question which I ask all physicists and scientists like you. Do you, at this stage, get the sense that the universe is really messing around with us?
no, I don't feel like that. But it does point to the fact that humans have been around a long time, and we're slowly learning, and it takes a lot of time to put the pieces together. And the rarer things are, uh, you got to learn, you got to take baby steps and learn. Slowly, we put the pieces together.
Right. Famously, Dr. Steven Weinberg, and I think I'm quoting him right, he had said that the more the universe seems comprehensible, the more it also seems meaningless. I tend to agree with that view so far because it's difficult for me to wrap my head around the purpose to this monstrosity that we call the universe. It's almost as if somebody is fooling us 24/7.
It's I feel more like we just don't know. We're ignorant.
Okay, okay. On that note, Professor Mathews, I thoroughly enjoyed talking to you. I hope it
Oh,
was worth
likewise.
your while.
Yeah, this was great. Thank you very much. I appreciate the time to come and chat with you.